Joke. York is from Princeton University. He's a colleague from the Pear Lab and a physicist with wide-ranging interests. And I am looking forward to seeing what he has to say about advanced propulsion and conservation laws. York.
Okay, well, let me begin by talking about what this talk is not. I'm not going to be discussing warp drives or any other technique for moving faster than light. When I use space propulsion in the title, I simply mean taking an object, preferably a spacecraft, and getting it to move through the three-dimensional space that we're all familiar with at speeds slower than light. So, as an outline, there are a number of systems that we know for space propulsion that are in use, and I describe them as having failings because generally they do less than we'd like. I'm going to discuss why some of these failings seem to be mandated by physical law, some theoretical alternatives that may allow better propulsion systems to exist. I'm going to review some specific proposals for such systems. But I ask the audience to remember that all of these specific proposals are speculative. So let's start with the basic rocket. You move something through space by throwing mass away in one direction to accelerate in the other direction. This is all in accordance with Newton's third law and the conservation of momentum. Now, they're not usually called rockets, but I am classifying ion drives, plasma drives, even exotic speculations like an antimatter neutrino drive as basically rockets because they all work this same way. Now, if conservation of momentum holds, the rocket is in fact the only possible completely self-contained space propulsion system. And somewhat annoyingly, all rockets suffer from the rocket paradox. Here's an example. We've got exhaust velocity, the speed at which you're ejecting matter, plotted across the bottom here, maxing out at the speed of light because you can't throw anything away any faster. Mass consumption goes down, energy consumption goes up. The more efficient your rocket is in terms of its use of mass, the less efficient it is in terms of the use of energy. In addition, there is the rocket equation. The velocity at which you throw away your reaction mass is pretty much a constraint on how much you can maneuver, on what total change of velocity you can accomplish. Specifically, the total mass of fuel you need, or rather the ratio of your fueled mass to the payload mass you're trying to move, grows exponentially with the ratio of the delta V, the velocity change you want to accomplish, to the speed at which you're ejecting the fuel. The blue curve here is a plot of the rocket equation in dimensionless units, just the ratio of your desired velocity change to your exhaust speed. These other straight lines are based on the chemical rockets we're building these days. The green line is the minimum requirements for velocity change for a planetary mission such as NASA is conducting right now. And the red horizontal line is our maximum engineering capability in terms of how much fuel we can cram onto the thing in terms relative to the mass of the structure required to hold it. The fact that this intersection is below this intersection is what makes planetary missions possible, and the fact that they're so close to each other is what makes them so slow and expensive. So if conservation of energy and momentum forces the rocket paradox onto any self-contained drive, what about systems that aren't self-contained? We've seen allusions to some of these in previous talks. Light sails get thrust by reflecting radiation from an outside source. The Bussard ramjet, we saw it discussed as a fusion ramjet. I like to credit the guy who seems to have come up with the original idea. You scoop up the ambient medium as fuel. Current-carrying tethers get thrust from exploiting ambient magnetic fields. Magnetic sails get thrust from deflecting ambient plasma. The ramjet may be impossible. Collecting interstellar hydrogen is a hard problem in itself, and getting it to undergo fusion on the fly is even harder. All of the other systems are dependent on special environments or support from home. The core problem that makes all of these drives unsatisfactory, unfortunately, happens to be two basic laws of physics: conservation of energy and conservation of momentum. Now, in relativity, these are the same law. Energy and momentum form a relativistic four-vector, and all of its components are conserved. Unfortunately, you can't escape the problem just by rejecting relativity. There's something called Noether's theorem in mathematical physics, a very long-standing result. It's a mathematical proof that any continuous symmetry in a physical law leads to the existence of a conserved quantity. The result of having physical laws that don't change over time is that total energy has to be conserved. Similarly, momentum conservation follows from the fact that physical laws don't change when you move from one place to another. I step from here to here. The laws of physics are the same in both places. Therefore, momentum is conserved, according to Noether's theorem. But there is a loophole. The tensor calculus used in general relativity satisfies the defining symmetries of general relativity automatically as a matter of notation. The Noether construction becomes trivial. It doesn't allow you to compute a conserved quantity. In fact, energy and momentum conservation in general relativity have only been proven for simple special cases. There is no general proof. So the conservation laws may not hold for the full theory. In fact, when you're dealing with an arbitrarily curved space-time, such as is allowed for the theory, it becomes a little bit difficult to figure out what something like an energy density even is, let alone whether it's conserved. Digressing for a moment, for most of this talk, I'm assuming that both special and general relativity are true. Now, there's a lot of evidence for this, and any alternative theory, if it is to be taken seriously, has to match a tremendous body of observational evidence that confirms both special and general relativity. However, since there are some anti-relativists around, especially in the SSE, it seems important to consider alternatives, at least briefly. Now, general relativity is mathematically unique. It's the only theory that, satisfies the appropriate symmetries, except for little bells and whistles like whether or not there's a cosmological constant. If GR is wrong, there's no way, I should qualify that, there's no way that I know of, to avoid the Noether construction, and we're stuck with conservation laws that are technologically inconvenient. However, a non-relativistic theory, by definition, admits the possibility of non-local interactions that propagate faster than light, which can create the local appearance of momentum non-conservation by having reaction forces apply to remote objects. In the most extreme case, a non-relativistic theory might allow instantaneous reaction with the entire background universe. The local acceleration of the drive might be obvious, but the reaction of all other matter everywhere would be impossible to measure. In fact, if Mach's principle is valid, it doesn't really have any meaning. Mach's principle, which has been mentioned several times for people who haven't heard of it, is simply the idea that it's the behavior of the matter in the universe as a whole that defines what is an accelerating or non-accelerating frame of reference. So, getting back to relativity. If general relativity is correct, the door may be open to violating momentum conservation This would allow non-rocket drives that don't need to throw mass away to accelerate. Candidates worth examining in detail: manipulation of inertia, manipulation of gravity, and then getting somewhat farther out, manipulating tachyons or violating the weak energy condition, which is a rather enigmatic statement that I'll discuss in more detail later. So, one thing that even a lot of physicists don't notice unless they've researched the topic, there are actually three fundamental definitions of mass. Inertial mass, that's the m in Newton's famous F equals ma equation. It's the resistance of an object to acceleration. It's the original quantity that got called mass. Gravitational mass, also due to Newton about 20 years later, is both of the m's that appear in Newton's gravity formula. It's how strongly an object attracts everything else. Energy content mass is the m in Einstein's E equals mc squared. It's the total energy content of a system divided by the speed of light squared. Okay, sorry about the typo. Now, all three of these masses are exactly equivalent, but nobody really knows why unless you simply take it as an assumption. And we certainly don't have any demonstration that this is always true. Now, for inertia, inertial reaction force is the force that resists any attempt to accelerate an object, the equal and opposite reaction in Newton's third law. Most physicists assume that inertia and inertial reaction forces are innate to mass. They're just part of what mass is. It's what it means to say that something's a massive object. However, some physicists wonder why these reaction forces exist and speculate that it might be somehow extrinsic rather than intrinsic, in which case it might be possible to manipulate whatever external factors cause it. Now, manipulating inertia automatically violates momentum conservation. The definition of momentum uses the inertial mass, so if inertial mass changes, momentum changes. However, manipulating inertia can do more than just mess up the bookkeeping. It allows you to construct the ultimate space propulsion device. Okay, now that everybody's had their giggle, why am I calling a wagon wheel the ultimate space propulsion device? Inertia manipulation lets you turn a rotating wheel into a space drive. Now, every spot on the rim of a rotating wheel is being accelerated inward and exerts an outward reaction force. Normally, all of these forces are in equilibrium. Even an unbalanced wheel just shakes as it spins. Over a full cycle, there's no net average force. It just rattles around back and forth. Now, suppose you can manipulate inertia. Specifically, suppose you can manipulate inertia in one part of the wheel, either by affecting a volume of space or by doing something to the wheel's components themselves on the fly as they pass through the target area. Well, for this example, we're increasing inertia in this zone. The ratio of acceleration to reaction force changes. We have a bigger reaction force. These are no longer in equilibrium. The whole wheel is going to accelerate that way. It will be pulled toward a zone where inertia is increased and away from a zone where inertia is decreased. And this is without expelling mass, without any other involvement. Simply the change in inertia, if you can do it this way, will have this consequence. Now, one candidate for inertia manipulation. In 1994, Bernie Heisch, who I believe is in the audience, Alfonso Rueda, and Hal Puthoff published a theory that inertial reaction forces are a result of electromagnetic zero-point fluctuations interacting with matter. Now, in the spirit of full disclosure, I co-wrote a couple of papers with some of them a few years later on this theory, so I'm not entirely unbiased. But the ZPF can be manipulated, and in principle, this could change the inertia of objects within the manipulated volume if this theory is true. Now, the one way we know to manipulate ZPF reliably and it's been referenced before and is going to be referenced again, is the Casimir Effect. Parallel conducting plates exclude some of the ZPF modes from the space between them, specifically the modes that are too big to fit. The reduced ZPF inside pushes out with less force than the normal ZPF outside pushes in. So it looks like there's an attractive force pulling the plates together that gets stronger the closer they are because you're excluding more modes. This has been confirmed empirically. So that leads us to what I've labeled the high-Schroeder put-off Casimir inertial wheel. If the ZPF is the source of inertial reaction, the reduced ZPF between Casimir plates should reduce the inertia. So you put plates on one side of the wheel, you get a reduced inertial reaction force, the wheel accelerates in the direction away from the side with the plates. Unfortunately, the ZPF change made by Casimir plates is in the wrong part of the spectrum to affect inertia very strongly. Making wildly optimistic estimates about our precision engineering capabilities, the best HRPC wheel with current technology would accelerate at 2 times 10 to the minus 27th power meters per second squared. That would need to operate for 1,000 years to travel a distance equal to 1 wavelength of visible light. This is not exactly a practical drive. Another candidate for inertial manipulation, for brevity I will just be calling the Woodward effect. Since the early 1990s, James Woodward has been publishing a theory based on Mach's principle that predicts transient changes in the inertia of devices, of objects whose density is changing. Some of his papers also contain experimental tests of the theory. His latest, at least the latest that I found in 2010, so I hope it's the most recent, notes that earlier experiments have given conflicting results, but the most recent experiments continue to support the theory. Well, here's the theory in extremely brief form. He ultimately ends up deriving this equation for transient inertial mass changes. It relates the rate of change of energy density, both the first derivative and the second derivative, to a transient change in the inertia of an object. The thing is, from his own derivation, you could just as well write this in terms of a changing mass density. This E naught is equal to rho naught c squared. So you can take out the c squared factors, write things in terms of mass density, and you get this equation, which is fundamentally the same equation. He even uses the equality rho naught c squared equals E naught in a couple of steps of his derivation. Now, because Woodward writes his equation in terms of a changing energy density, all of his experiments have involved charging and discharging capacitors to change the energy density. The measurements involve oscillating the capacitors back and forth in time with the charge and discharge to look for a net static thrust from the changing inertia. Looking for a net thrust in this kind of vibrating apparatus is notoriously prone to experimental confounds, which is probably why the conflicting results mentioned in his latest paper have come about. His 2010 report uses a rotating mount, but because he's cycling the capacitors at a much higher frequency than his rotation rate, he's still looking for an oscillatory effect. However, it seems like the Woodward effect should be ideal for the inertial wheel configuration. Because the inertial transient is driven by changes in mass density, all you need to do to alter one section of a rolling wheel is to compress it. Now, funny, when does one section of a rolling wheel get compressed? Well, that happens when ground vehicles roll on tires. We've got a natural experiment out there in the world for over a century. Modern pneumatic tires like this one don't test the effect. The pressure is distributed and there are no transients. However, in the early 1900s, many cars used solid rubber tires. Well, at least some of them did. There was a lot of experimentation in that era. those do go through local compression cycles as the wheels roll, creating rapid changes in density. The Woodward transient works out to be negative, so the reaction force induced against the tire rotation is directed upward. So in the reference frame of the car, the wheels spin, they generate inertial reaction at every point on their rims. The road rolling by at a speed that matches the wheel rotation, remember we're still using the car's inertial frame here, compresses the contact point, creating a Woodward inertial transient for each segment of the wheel as it comes into contact with the road. This transient is large and negative and increases as the fourth power of the car's speed. According to the Woodward's equation, a typical 1900s vintage car with solid tires should have launched itself into the air once it hit a speed of 4 miles per hour. At best, this indicates that the Woodward effect is weaker than the equation suggests, which, in fairness, does correspond to some of the results Woodward has gotten. They've noted a smaller inertial transient than the equation as written at face value. Hello? Thank you. Another route to propellantless propulsion is the manipulation of gravity. Now, we've seen Einstein's field equation for gravity before, and I want to concentrate on the source term, which is called T mu nu. It's called the stress energy tensor. In addition to energy, it contains terms for momentum, energy and momentum flux, pressure, and shear. Now, a question, does pressure have inertia? Einstein's E equals mc squared was basically a demonstration that energy has inertia. You can write it as m equals E over c squared. It's not immediately obvious whether Einstein's proof applies to all terms in T mu nu or only to the energy terms. So for the moment, we're going to assume that the pressure terms in T mu nu don't add to inertia. Then we can decouple inertial mass from gravitational mass. Internal pressure will make an object create a stronger gravitational field without changing its inertia. Now, briefly discussing the nature of gravity, force, and acceleration in general relativity. Gravity is not a force. Gravity is space-time curvature that makes a free trajectory look to a distant observer as if it's accelerating. Right now, you're sitting still on Earth. The surface is forcing you to accelerate away from the curved space-time path that leads downward toward the center of the Earth. Your weight is an inertial reaction force. There's a natural free fall trajectory that leads downward. There's a non-gravitational obstacle forcing acceleration away from that free fall trajectory, this imposed acceleration, and there's an inertial reaction, which we call weight. So now let's look at a couple of spheres in empty space. They each have their own mass, and we're holding them apart mechanically with a strut that has negligible mass, and we're just using it to impose a non-gravitational acceleration on the system. Specifically, we're using it to hold these things at rest when they want to accelerate towards each other. So the imposed accelerations are different, assuming that m1 is not the same as m2, but the inertial reaction force turns out to be the same, because this acceleration is proportional to m2, the mass is m1, you get gm1 m2. Down here, acceleration proportional to m1, inertial mass of m2, you've got gm1 m2 again. The inertial reaction forces exerted on the strut are identical. Everything's in balance, nothing's going anywhere. Now let's pressurize m1, keeping its mass the same. By hypothesis at the moment, the pressure won't increase m1's inertia, but will strengthen its gravity. Now, this imposed acceleration has become bigger. This inertial reaction has become bigger. This one is still the same because pressure does not contribute to inertia, we're assuming. The forces are out of balance and the whole system's going to accelerate. Unfortunately, gravity is a weak force to begin with, and it takes a lot of pressure to rival the gravitational effect of mass. There's a factor of c squared involved. The strongest materials available, currently known, compressed to just short of their yield strength, will have a pressure contribution to their gravity of about 10 to the minus 11th. That's 10 parts per trillion. The unbalanced gravity drive at this level will accelerate at 5 times 10 to the minus 17th meters per second. That actually depends on the total mass of the system, so I'm throwing in an assumption that you don't want to try to build a spacecraft that weighs more than a few tens of tons. Now that's 10 orders of magnitude better than the last one we looked at, but it still needs to run 73 days to travel 1 millimeter. Now, we've been supposing for a while that pressure doesn't have inertia, but suppose it does. Then the unbalanced gravity drive doesn't work because the extra gravity source has its own inertia. Inertial mass and gravitational mass stay coupled. But this uncouples inertial mass from energy content mass. And this should sound familiar because it means you can change inertia without changing the energy content mass, the amount of stuff, if you will, in an object. A self-contained pressurization system won't change the total energy content, but it can still add or remove pressure. If pressure has inertia, we can manipulate the inertia of objects on the rim of a rotating wheel. Now, once again, with the best available materials, this version of the inertial wheel could accelerate at nearly, I won't recite all the zeros, this is half a microgravity. That's 11 orders of magnitude better than the unbalanced gravity drive. So one way or another, it looks like we have violation of momentum conservation. If the pressure terms in the stress energy tensor contribute to inertia, then we can build an inertial wheel drive. If they don't contribute to inertia, we can build an unbalanced gravity drive. So now we'll go farther out into speculation. For somewhat over 40 years, physicists have speculated about tachyons, hypothetical particles that always move faster than light. They're a marginally respectable topic in relativity, and they're an abomination in quantum field theory. Although they're consistent with relativity and respect conservation laws, their FTL movement means that, like non-relativistic interactions, they can create the local appearance of non-conservation. So some properties of tachyons: this factor, square root of 1 minus v squared over c squared, is ubiquitous in relativistic transformations, and if v is bigger than c, it becomes an imaginary value, which is why it's usually considered to be meaningless to talk about having something move faster than light. However, if the rest mass of an object is also imaginary, the imaginary factors cancel, and the mass, momentum, and total energy of such a particle become real values as long as it keeps moving faster than light. Fundamentally, you get 3 kinds of particles. We're made of particles that are sometimes called tardions, so we know they exist. We interact with massless particles all the time, so we know that there's no barrier to interactions between 2 different kinds of particles on this chart. Tachyons, if they exist, would simply add another category that covers the remaining velocity regime. We've got always slower than light, we've got always moving at the speed of light, we've got always moving faster than light, and all of them have real total energy. Now, both tardions and tachyons gain energy and momentum as they approach the speed of light. Now, as they slow to rest, tardions lose all of their momentum, but still have a minimum energy, their rest mass and its associated energy content. Now, moving close to the speed of light, tachyons look similar, but as they accelerate to faster and faster speeds, they do something different. It's their total energy that goes to 0, and their momentum that goes to a minimum value. So in terms of space drives, a tachyon would be a something-for-nothing particle. You can create, if you can create them in the infinite velocity state, the instantaneous propagation state, they have 0 energy and non-zero momentum. You can generate thrust while expending no energy. That same 0 energy state is why quantum theorists hate tachyons. Any theory that allows tachyonic states predicts an infrared catastrophe where infinite numbers of 0 energy tachyons get generated. The reason string theorists require extra spatial dimensions is to prevent any string states from being tachyons. If you try to do string theory in just the 4 dimensions we think we know about, you discover that the lowest energy string state is a tachyon, and this makes field theorists very, very unhappy. And let's go even farther out for a moment and consider negative mass. The weak energy condition, which I mentioned before, is a feature of general relativity that does not follow from the field equations, but is a constraint on what sort of values are allowed in the stress energy source term of the field equation. There are several energy conditions, and all of them are not conclusions of general relativity, but rather expectations, I tend to think of them these days as pious hopes, about what sorts of situations are permitted by non-gravitational physics. The weak energy condition, expressed in words, says that energy densities can't be negative. Unfortunately, it's already known to be false. The Casimir effect demonstrates the existence of a negative energy density. Now, it's believed, though not proven, that a suitably averaged form of the weak energy condition still holds in the Casimir effect, but in its raw form, the condition does not. So even this partial and provisional violation prompts speculation that the principle simply may not be true. So, what if the weak energy condition is not a universal rule, but a biased extrapolation from our limited experience? Then it may be possible to create configurations of matter and fields that have negative total energy. They would therefore have negative mass and negative inertia. An object with negative inertia accelerates in the opposite direction to an applied force. Now, let's think about a spacecraft attached to an object of exactly equal negative mass. If the craft now pushes the negative mass backwards, the reaction will cause it to accelerate forward. The object with negative inertia will react to the backward push by accelerating forward at the same rate. No conservation law is violated because the total energy and momentum of the system remains zero no matter how fast it's moving. Now, why this is unlikely? Quantum systems tend to decay into the lowest energy state available, releasing energy. If negative mass states are possible, they should be ubiquitous, but we don't observe them. The negative energy density of the Casimir vacuum isn't a violation of this statement of non-observation because it is only stable under boundary conditions that embody much higher positive energy densities, so the system as a whole requires positive energy to construct. So, an overview of the theory. I hope I'm on time here. Current space propulsion systems have very limited capabilities. Better technology can improve this, but any rocket-type drive will be limited by conservation laws. Alternatives to the rocket that are also bound by these laws have unsatisfactory features, but there are valid theoretical reasons for suspecting that these conservation laws may not actually hold, or it may at least allow apparent local violations. Now, even if the theories justifying these speculative drives are true, useful application is out of the reach of current technology. Now, I find it interesting that several of these drives can be improved just with advances in material science rather than more exotic technologies. Some of them may be testable or nearly to the point of being testable with space-based experiments. And that's the end of my talk.
Thank you, York. Not only on time, but we have a little more than 5 minutes for questions. Bernie?
Just a quick question, York. Could you elaborate on the infrared catastrophe you'd mentioned? I didn't catch what that was about.
Okay, the infrared catastrophe is basically because there is a state in which a new tachyon can be created without any expenditure of energies. When you study the Feynman diagrams for potential tachyonic interactions, you basically find an infinite cross-section for emitting tachyons in a certain state. This leads to something like a direct vacuum hypothesis where the cosmos should already be full of tachyons in a certain state of motion. And of course, because we don't actually have a good theory for tachyon interactions, we don't know what exactly that universe would look like, but we don't think we're living in it. Oh, it's called infrared because it involves dropping to zero energy. It's in contrast to the Jeans ultraviolet catastrophe.
York, I think that the solid rubber tire model might be recoverable so that the theoretical models are not disproven, because the compression and expansion of rubber has hysteresis that shows up as heat. The energy gain that supposedly was coming from this was instantly being dissipated just in the heat and the rolling of the wheels.
Well, the issue with the compression and expansion doesn't relate to energy as such, but to the inertial transient. The work done on the tire, which is where the heat comes from, that then has to be dissipated. Yes, that's changing the energy density, but that is many orders of magnitude smaller than the change in the mass density created by the compression of the rubber. Therefore, at best, that becomes a minuscule correction. Now, it's entirely possible that there are other considerations in the theory that avert this difficulty, but as it stands, the equation as written seems to be making a very odd prediction.
What if things are not continuous?
What if things are not continuous? Could we be a little bit more specific here?
What if space and time are discrete?
If space and time are discrete, it becomes very difficult to understand some aspects of the Lorentz transforms. And of course, general relativity itself is written in the form of a field equation on continuous quantities. To construct a discrete version, you have to make significant changes in the theory. Since I was working within the context of that theory, I didn't really look into how the discrete alternatives would work.
York, I can't speak with authority on this, but I worked for a company that made closures for vials of injectable drugs, and they typically were composed of a molded rubber stopper and an aluminum cap that held the stopper in place. And my colleagues in the rubber division of that company insisted that rubber is not compressible. It's like an elastic, incompressible liquid. I've never proved it myself, but it might be something to consider.
Strictly speaking, there is no such thing as an incompressible material. Every material has a Young's modulus. None of them has yet shown up with one of infinite value. Therefore, when you apply pressure to things, you can compress them to some extent.
One more question.
Yeah, York, maybe we can clarify that. When it comes to compressing things, you use the bulk modulus, and you probably want to compress it from all directions, like put it in a pressure chamber. But if you squeeze it in one direction, it can squeeze out in another direction. And I think that maybe that's what he's referring to, in which case, if you push the tire down in one direction, it can squeeze out in another direction without necessarily compressing. Maybe that's what he's saying.
That might very well be a process that is happening, and I would expect it to be happening, but in a solid rubber tire under lateral compression, the rubber to either side of the compressing force has to be contributing something to holding it in place and creating an actual density increase, or else it would rip free from the underlying wheel.
Okay, thank you very much.